Okay, we're going to talk about the overall energy and entropy balances for a Carnot process. And that helps us actually determine the overall efficiency of the system. But let me first draw what I'm talking about. You've seen this already, assuming you're either taking my class or watching my earlier videos. So we have a boiler that produces vapor from liquid, takes us to state 2, from 1 to 2, with the high pressure vapor produced by the boiler. We have a turbine that extracts work. By the way, the boiler needs to have input heat. I called it QB earlier, but I'm going to call it QH now. Okay, the turbine takes us to state 3, and that's a low pressure vapor. We're going to condense and extract QH. Then we're going to use a pump and put in work to close the loop. Condenser produces state 4, and the and the pump takes us back to state 1 so that we have a fluid that we can take around in circles and run continuously to produce what we want. What we want is work from the turbine, and we get it by burning fuel. So hopefully you can see that work from the pump is necessary, because it is necessary to bring the loop back to state 1. But we haven't really illustrated why QH is necessary, although I guess you can make a similar argument there, right? That it's necessary to remove some of the heat in order to bring the fluid back to liquid state. I'm going to summarize this process the way Carnot did. The way he put it, he said that there's a hot reservoir that is transferring QH into some sort of cycle, and that cycle produces work. I'm going to call it W net, because that is equal to minus work of the turbine, shaft work of the turbine, and that's going to be minus the shaft work of the pump. I get tripped up with signs. The work of the turbine is actually negative because it's coming out of the system. So minus work of the turbine is positive. The shaft work of the pump is positive, but we subtract it because it's not our desired output. It's a cost of doing business. Okay, now we also need to reject heat into the surroundings. So I'm just going to separate these. I don't mean to imply. They're both two ways of drawing the same thing. It's not like this is not meant to connect to that. The question that I want to answer here is, well, I mentioned why is QC necessary, but also how much work can I get by burning fuel? I also want to point out that enthalpy and entropy are state functions. So if I'm working with a cycle, that means that the delta H of the cycle, my system, my working fluid, has to equal the delta S of the system, which is equal to 0. Because they start at state 1, change states, and then come back to state 1, the net delta H and delta S is actually 0. Okay, so let's do an overall energy and entropy balances. we have to obey the first and second law. So the delta U of my cycle is going to be QH. Actually, I suppose that's actually the delta H of the cycle. It actually doesn't matter. I think it's the delta. That's actually true about both. Well, my notes say delta U, so I'm going to stick with delta U. Because there's nothing flowing in or out of the system as we're drawing it. It's just things are flowing in and out of the individual units. And we have QH, we're taking out QC, and we have W net, right? The turbine minus the pump. And we know that this is 0. Let's do an entropy balance. So the delta S of the universe is 0 because we're assuming it's a reversible process. And that is going to be minus QH over TH, which is the entropy lost by the hot reservoir. So this is the delta S of the hot reservoir. That's this entropy loss due to heat exchange. And then the cold reservoir is going to gain entropy because it is actually receiving heat. And then there's the delta S of the engine, my system or cycle, and this is 0 for a cycle. Okay, so what does that tell us? Well, a little algebra will show that TH QC over TC minus QH equals 0. And now we can plug in the first law of balance. This is going to equal QH is going to equal W net plus QC. Okay, so that implies that TH over TC QC minus W net minus QC is equal to 0. Or W net is equal to QC TH minus TC minus 1. This happens to equal TH over TC minus TC over TC. That's equal to QC TH minus TC over TC. Okay, so notice that, remember I said that it's not obvious why QC is necessary here, okay? Well, it turns out that when you do all the balances, you find out that we get no work out of this process unless we extract heat, QC. So it is a byproduct. It's not an intended thing. I mean, we would love it if we could just burn fuel and convert that completely into work, but it turns out that that's not actually possible, right? And we can also express this in terms of energy. So if we say the efficiency, express this in terms of efficiency, not energy, although energy is involved. Our desired output is W net. Our required input is QH, right? And we know that QH is W net plus QC from the first law balance. So then this would equal QC TH minus TC over TC over QC plus QC TH minus TC over TC. Maybe you can see where I'm going with this. The QC's will all cancel, and TH minus TC over TC divided by 1 plus TH minus TC over TC multiplied by TC over TC. That's going to give us TH minus TC over TC minus TH minus TC. The TC's cancel. So this is going to be, sorry, I did something wrong here. TC, this is a plus. Yeah. Okay, so this is going to equal TH minus TC over TH, which could also be written as 1 minus TC over TH, which is our efficiency. So this is a famous equation that tells us that according to the Carnot heat engine, efficiency depends on the ratio of TC and TH. So note that if if TH is much greater than TC, then eta is approximately 1. So if you can reject the heat at a much colder temperature or much lower temperature than your fuel temperature, fuel burning temperature, then you'll get close to 1 efficiency. So let me summarize with a few observations. I've already said these things, I think, but eta gets close to 1 when TH is much bigger than TC. QC is necessary for power generation. That's a consequence of the energy and entropy balances. Another way to put it, I didn't say it this way, but if we say the delta S of the universe is equal to minus QH over TH plus QC over TC, which is equal to 0, what it means is that QC would be 0 if QH, or the other way around, QH would be 0 if QC is 0. And so also W net, which is our desired output, is going to equal QH minus QC. So QC equals 0, which means that QH would be 0, would also mean that W net is 0. I think that's it for my discussion of the Carnot process. The next step is going to be to talk a little more about what happens in reality and present the Rankine process.